Let's go over the in-class activity answers for Equilibria Part D. So in question 1, we're asked to consider the following reaction, and they tell us it's equilibrium. So the double arrow tells us that it's at equilibrium. So the forward direction is going just as fast as the reverse direction. And they want to know, what's the effect of adding SO3 on the system? So we're going to be applying Le Chatelier's principle. So Le Chatelier's principle says that once you disturb the equilibrium, the reaction is going to try to undo what you just did so that it can go back to equilibrium. So if I add more SO3, so I'm going to throw it off. So now my Q, I've got a Q instead of a K because I'm no longer at equilibrium because I've added SO3. So I've increased that concentration. Now I need that Q to come back down and match the K value. So the only way to do that is to go in the reverse direction. So we're going to decrease the concentration of the SO3, decrease the concentration of NO as we go back to the reactants, and that's going to increase the SO2 concentration in the NO2. So that's going to bring that Q back up so that it matches the K value. Or sorry, it's going to bring it back down so that it matches the K value. So if I increase the products, it's going to shift towards the direction of the reactants. Now we're looking at the same reaction, but what's going to happen when we remove NO? So if we remove NO, we're going to have to do something to replace the NO that we took away. So think about if you were having to bring cookies to a family get together and you said you were going to bring 32 cookies so that there's one cookie for everybody at the party, and your dog eats 6 of the cookies and you're like, oh no, what do I do? Well, you have to make more cookies. You have to switch. The equilibrium has to shift to replace what was done. So if we lost some of the NO, we're going to have to make more. So we're going to shift to the direction of the products and make more of the reactants. So the reaction will shift in the direction of the products. Okay, same system again, but this time we're looking to see what happens if we add CO to the system. Now notice CO is not part of the equation. It's not part of the equilibrium, or else it would be expressed in the reaction equation. And also too, the other thing, CO is a gas. And so adding a gas will change the pressure, but because we have the same number of moles of gas on both sides, that's not going to change anything. So if CO is not part of the K expression, because the K we said is products of reactants, the NO times the SO3 divided by the NO2 divided by the SO2, since K is not, the CO is not part of that, it's not going to do anything to the reaction. So no change will occur. And 4, we've got CO2 combining with water to make methane and oxygen, and they give us the delta H. So they want to know what's the effect of increasing the temperature on a system. Now remember, those equilibrium constants, they're constants. So, but they're unique for a particular temperature. And so this time we're going to look at see what happens when we change the temperature. And we first have to look at the delta H. So the delta H is positive. Positive means we're depositing energy into our system, just like we're depositing money into our bank account. So that's money going in or energy going into the system. So that's an endothermic reaction. So if it's going in and it's endothermic, then that means our energy is going to be considered as a reactant. So I like to just write it as part of the reaction equation. So I'm going to put my energy on this side of the equation because it's going to be a reaction like it's endothermic. So that means if I increase the temperature, I'm increasing one of the reactants. And so if I'm increasing one of the reactants, I'm going to shift towards the products. I'm going to try to undo what I just did. So I need to get rid of some things. So the reaction will shift to the right in the direction of the product. So same reaction again, but this time we're going to look at decreasing the pressure. And so remember, decreasing the pressure, think back to your ideal gas laws. So there's two ways that we can think about doing this. We can either remove some of the gas, so remove the number of moles, or we can increase the volume. And so that's how we can decrease that pressure. And so as we decrease the pressure, the concentration of the gases gets smaller. So there's more empty space. So if there's more empty space, the reaction's going to want to shift to give whichever side needs the more room. So look at this reaction. On this side, I have 1 mole of gas. So this is gas and this is liquid. On this side, I've got 3 moles of gas. So 1 mole here, 2 moles here, so a total of 3. And remember, gases take up a lot more room than liquids. We're not even considering the volume of the liquid here. Also too, that liquid is pure. So as we look at this, we've got 3 moles of gas. So decreasing that pressure, that means there's less gas molecules hitting each other, and because we've got like a bigger space, or it's less dense. So we can accommodate the more particles. So in this reaction, the reaction will shift to the right in the direction of products. It shifts to the side with the more moles of gas. So remember, if you have questions on any of these, please feel free to come talk to me during office hours or in class when we're doing discussion time, or before or after. So don't be afraid to get help if you're not understanding some of these concepts.